welcome to a course on measure theory and integration. In this lecture, we are about to start the concept of Lebesgue integral. Okay, so before in the initial lecture of this course, I have given you the ideology of how Lebesgue extended his ideology from Riemann integration. Let us now revisit few things about Riemann integration and then we'll come to the concept of Lebesgue integral. So as I said, we are about to start with the concept of Riemann integration. So let AB be an interval which is taken in the real line. Okay, and F is some bounded real valued function which is defined on the interval AB. Okay, now let us choose A to be xi naught and in between we are choosing some other points xi1, xi2 etc. till xi n is nothing but B. Be a subdivision of AB. Okay, what we have actually done here is that we have the interval AB. In between we have introduced few points and named them as xi1, xi2 till xi n minus 1. Okay, in between we have introduced n minus 1 points so that this entire interval is subdivided into n subintervals. Okay, they need not be equally distant. They need not be equally distant. You can introduce any n minus 1 points in between them with the condition that your xi1 must be smaller than xi2 and xi2 must be smaller than xi3 and it goes. Right? So this A we take it as xi naught and this B we take it as xi n, so that this will have the uniform notation. Okay, so we have split things like this. After splitting things like this, what we are going to do? Then we will define mi to be the supremum value in the subinterval in this subinterval. Okay, supremum of the function in this subinterval and small mi be the infimum of the function in the same subinterval that we have chosen. Okay, after this we are about to define something called upper sum and lower sum. What are they? That is, okay, let me denote big S as summation I runs from 1 to n mi multiplied with xi minus xi I minus 1 and small s as summation I runs from 1 to n small mi xi minus xi I minus 1. Okay, the corresponding supremum and infimum value in the subinterval has to be multiplied with the corresponding length of the subinterval. We after finding in the each subinterval we'll have to add them up. That is what we denote it as biggest and smallest. Then with the help of these two things, then we define the upper Riemann integral as integral A upper bar B. This is not minus B, this is integral upper bar B. Okay, it is upper Riemann integral of the function f of x dx as infimum of the upper sums. Okay, here this quantity is called as upper Riemann sum and this quantity smallest is called as lower Riemann sum. Okay, here you have just taken only one sub, like you have just found only one type of subintervals. Okay, in this way we are able to find out any possible number of subintervals. In that case, we'll have to take the infimum over all possible subintervals. Okay, the intermediate points that we have introduced to split the entire interval into subintervals, that only the collection of those points alone is called as a partition. So this infimum is taken over all possible partitions. Okay, so in this fashion only we are defining the upper Riemann integral, and the lower Riemann integral is defined as, it is quite similar. There we'll have the lower bar f of x dx is nothing but supremum of all possible lower sums. Okay, so with the supremum and infimum which are taken over all possible subdivisions. Okay, here there are few points which are to be noted. They are the upper Riemann integral, the value of the upper Riemann integral. So by integral, what we mean is that it is basically an operation. After performing the operation, we will be having a value. Okay, the upper Riemann integral value is always greater than or equal to the value of lower Riemann integral. Right, and if the two integral values are equal, okay, if the two integrals are equal, this common value is called the Riemann integral of function f, and is denoted by r f of x dx. So here I am just writing r in order to specify that it is Riemann's work. Okay, it is Riemann upper integral, Riemann lower integral, Riemann integral. In order to specify that one, we are specifying this r. When you people studied these things in the course of real analysis, you might not have used this notation r. There, we simply write f as a member of R. So, when we say like this means this function f is Riemann integrable functions. And you might have come across this notation as well. This means the function is Riemann-Stieltjes integrable. Your Riemann-Stieltjes can be converted to Riemann just by taking the function alpha x to be equal to x. So these are the things that you have studied there itself. Okay, there we were dealing with only Riemann integrals, and that is why we did not have this r along with this integral symbol. Okay, here we are about to convert things into Lebesgue's approach. That is why we will deal with two different type of integrals. In order to specify it is Riemann's work, Riemann integral, we have this r before that. Okay, now we will define something called a step function. Okay, a step function by a step function, actually by a step function we mean a function psi which has the form psi of x equals ci for x value lying in the subinterval xi I minus 1 to xi I. Okay, for some subdivision of the interval a comma b. Okay, basically you will have to subdivide your given interval into subintervals. In each subintervals the function takes different values. Okay, and here we have some set of constants, and those constants we denote it as ci's, right? So this is what we have. Fine. So now with the help of the definition of Riemann integral we are about to do something. And that would be from the definition of the integral your integral of the step function over this limit would be summation I runs from 1 to n in each subinterval. Okay, what is the definition? We'll have to identify the supremum and infimum value in each subinterval. That has to be multiplied with the length of the subinterval. Here the length of the subinterval is xi minus 1, and in each subinterval the function behaves as a constant. So the supremum and infimum values are one and the same. So and that value was going to be simply ci, okay, the constant that we have chosen, multiplied with xi I minus xi I minus 1. So this is going to be the integral value of the step function over the given period, right? So here we have just integrated the step function. It can be any step function. Okay, and now with this notation we define the upper Riemann integral R of integral upper bar a to b f of x dx is infimum of summation I runs from 1 to n ci xi minus xi I minus 1, and this is nothing but infimum of xi of I integral xi of I dx for all xi of x bigger than or equals f of x. Okay, that is the upper Riemann integral R of integral upper bar a to b f of x dx is equal to psi of x dx just implies, or this is equal to the integral psi of x dx for some step function bigger than or equals the given function. Okay, similarly one can define lower Riemann integral of this function is equal to the some function phi of x dx with phi of x smaller than or equals f of x. Here this psi of x and phi of x are step functions, right? So if you are given any function, and if you have to integrate that function with Riemann's ideology, Then, in order to find the upper Riemann integral and lower Riemann integral, you can simply find a suitable step function satisfying the condition for all the points in the closed interval that we have taken. Then, with the help of the step functions, one can write the upper Riemann integral and lower Riemann integral. Okay, that is what is given here. So we are about this identifying this step function would be of great use when we extend things from Riemann's approach to Lebesgue's approach. Next, we are about to see the Lebesgue integral of a bounded function over a set of finite measure. Okay, so by this what we mean is that if we have a set which has the measure and that measure is a finite quantity, then how are we going to define the Lebesgue integral for that function? Okay, here first thing that we are going to see is canonical representation of the function phi. Okay, so if phi is a simple function, so we have seen the definition of simple function in one of the previous lectures. You can revisit and see what do we mean by simple function. And we have a collection of points a1 through an as a set of non-zero values of the simple function phi. Then this phi may be written as summation ai chi ai. Okay, where the big ai is the collection x such that this phi of x equals ai. Okay, this representation for phi is called the canonical representation and it is characterized by the fact that ai are disjoint and small a's are distinct and non-zero. So this is about the canonical representation of simple function phi. Next we are about to define the integral of phi, that is integral of this simple function phi. Okay, if phi vanishes outside a set of finite measure, in this case only we define the integral of this function phi by integral phi of x dx as summation I runs from 1 to n ai multiplied with measure of ai, where this function phi has the canonical representation f equals this function phi has a canonical representation, that is phi equals summation I runs from 1 to n ai chi ai. Okay, so this can also be denoted by simply integral phi. Okay, here let us make a note. If E is any measurable set, then we define integral over E phi is nothing but integral over phi chi E. Okay, so that is you have to express that measurable set. With the help of the measurable set, you will have to identify the characteristic function. You just multiply the characteristic function with the simple function that you have and do the integration. That's it. So that's it for today's lecture. In the upcoming lecture we are going to see few properties in the forms of lemmas and propositions for the Lebesgue integral. Till then, thank you.